All right. Okay, so we're going to start reviewing for our quiz. Again, our quiz will just be 2 FRQs. There will be one that is differential equation, and then the second one will be Riemann sums. Okay, and for your homework, you're going to see that as well. Two FRQs, one differential equation, one Riemann sums. Monday, we'll review again. All right, just going through the same, just going through additional practice, and then Tuesday is your quiz. Right. Okay, so a large vat is initially filled with saltwater solution. A solution with higher concentration of salt flows in the vat, and solution flows out of the vat at the same rate. The number of pounds of salt in the vat at time t minutes is modeled by the function a. So a represents the amount of salt. Okay. This satisfies the differential equation dA dt. At time t equals 10 minutes, that contains 50 pounds of salt. Okay. Write an equation for the line tangent to the graph at t equals 10. So we've seen this over and over again, tangent line equation. So we have to find order pair, we have to find slope. Now, typically, I know for tangent line equation, when you find order pair, you're looking for x and y, but we have to make an adjustment here. The variable provided for us is not in terms of x and y. It's in terms of t for time and a for pounds of salt. Right. If you see variables that you don't recognize, just always understand that there's always going to be that anchor t variable for you. Okay, you're never going to see a problem where a word problem where this the variables are q and v. It'll never be like that. It'll always be, if there's a word problem, it'll be time and then that other variable you don't recognize, that's going to be your y. So we see that at time t equals 10, that contains 50 pounds of salt. Okay, so 10, 50, that's our order pair. Okay, our slope is going to come from our derivative. So our derivative is dA dt. We'll just insert what it takes from our order pair. Doesn't take the 10, doesn't need the 10, it only needs the 50 for the a. So we can say dA dt. Typically, when we want to insert into a derivative that could potentially take multiple variables, we use this notation vertical line with an order pair to indicate that I'm trying to insert both variables into the derivative if it will take them. But in this case, it's only taking the a variable, which is fine. Okay, order pair, slope, and then next point slope form. Okay, typically, I know we do y minus y1, but we have to make an adjustment because of our new variables. So instead of y, we're going to use a. Instead of x, we're going to use t. Okay, so my 10 and 50 will insert for t sub 1 and a sub 1. And the m is obviously my slope 5 there. Okay, so let's get it into this form with the adjusted variables. Okay, so for a, right? So that's our tangent line equation. Okay, now the second part of a says use the tangent line equation to approximate the number of pounds at time t equals 12 minutes. Okay, so this is linear approximation here. All linear approximation is we're just inserting into the work that we've already accomplished, right? So just insert that variable 12 in for t, and that's our linear approximation. Okay, it's an approximation, so I'd use that squiggly line there. Use our calculator or just work this out by hand. 12 minus 10 is 2, 2 times 5 is 10, 10 plus 50. Okay, any questions so far? Okay, let's look at part B. Part B says, show that A of t satisfies the differential equation dA dt with initial condition A of 10 is equal to 50. Okay, so I think the easiest way to do this, I feel, I guess we could go from dA dt, try to find the antiderivative, but as long as we can show that we can get from one place to the other, I think that is sufficient. So I'm thinking that's easier if I just find the derivative. If I find the derivative, and then hopefully I can get this dA dt to maybe look like this as well. So either way, I'm just trying to resolve these two here, trying to get these two to look alike to show that they're the same, or that they're from the same function. Okay, so I'm going to start with A of t here. dA dt is a prime, so I'm just going to go ahead and find a prime. To find a prime, let's see. $300 becomes, what's the derivative of 300? Just what? Just 0. Okay. And then here I have e to the u, right? So the rule for e to the u is e to the u times u prime. Yeah, u prime. So 250 will stay. That's just a coefficient. Times, what's the derivative of my full exponent here? Yeah, just negative 0.02, right? 0.2 is a constant. It's just that linear, that coefficient from that linear term there. All right, let's see what that A prime looks like. I know A prime is another way of saying dA dt, but I just want to just show that this is my process from A of t, and I can look at dA dt in a second. Do a little bit of cleanup here. I can use my calculator. I can multiply this out, multiply the coefficients together. And negative 250 times negative 0.02 gives me 5. Okay, let's switch over to dA dt here. That's also given to us. We're just trying to get these to look alike. And right now, they're still a little different, right? These are technically the same, but I'm still not able to get it to look the same. But maybe I can replace A with something. What can I replace A with? A is just my equation, right? So the hope is that, well, if I make that substitution, maybe after I clean this up, I can get these to look, exactly alike. So I'm going to make a substitution for this A here. A is just my original equation. Okay, we distribute the negative, decimal through. So negative 0.02 times 300 gives us negative 6. Negative 0.02 times negative 250 gives us 5. And we're able to get them to match. So that's all this problem was doing, just trying to have us show that that one is the derivative of the other. Okay, so now part C is where we're moving into our solving differential equations portion. Okay, so let's look at part C. Part C says the flow of solution into the vat is stopped and the solution is drained. The depth of solution in the vat is modeled by the function h that satisfies the differential equation dHdt equals negative k root h, where h of t is measured in meters. K is the number of minutes since draining began, and k is a constant. K is a constant. If the depth of solution is 16 meters at time t equals 0 minutes, and 4 meters at time t equals 30, what is h of t in terms of t? So we're going to solve this differential equation. Again, I know that we probably prefer x's and y's, but if you see a differential equation, and it's not x's and y's, it's always going to be t and something else. So in this case, t is our independent variable. In this case, h is our dependent variable. The thing that looks a little bit strange is what to do with that k here. So that k is just a constant. We'll treat k like we would if it was a 5, 8, or 10, any other constants from other differential equations. But we're going to eventually have to solve for k. And that's why they gave us two sets of ordered pairs. One set of ordered pairs is going to help us solve for c when that shows up. But then they give us another set of ordered pair to help us with the k value. So that's why we're given those two sets of ordered pairs. But we'll get to that later. Let's focus our attention on just trying to go through our steps, right? So separate the variables through cross multiplying, moving terms around, and then eventually taking the antiderivative. Okay, so let's try part C here. Okay, so I like to force that second side, that right side, to be a fraction so I can see where my cross multiplying is going to occur. Okay, so cross multiply. I want my h's on the left and my t's on the right. Okay, so I like to do cross multiplying because I can at least get these two in their right places. And now I should decide, is there anything else that has to move? Is there anything else that's out of place? The root h. Okay. So the way we move that root h is we divide that root h over. Okay. The k is going to stay because remember we said that we only want what's on the left side, what is absolutely necessary, right? So we only want anything involving h's on the left side. Anything that is t related or anything that's coefficient or anything that's that's not needed, we'll go ahead and that doesn't have to be on the left side. We'll go ahead and leave on the right side. Okay. So all I'm going to do is divide that root h. And I should be able to achieve full separation here. Okay, remember k is just a coefficient. I'm going to pull that out in front. And hopefully helps us see things a little better if I just pull that k out and remind myself that there's only a 1 in front of dt. I'm taking the integral of both of these, both sides of the equations independently. Okay, so let's think about the rules here. How would you approach the left side? What rule can we use on the left side to find the antiderivative? Yeah, we got to rearrange it, and eventually we're going to apply what rule? Power rule. Good. But a couple of things has happened, right? The root h has to be rewritten. The h has to come onto the top. Now, why is this not natural log? Because a lot of times we use natural log if we see variable in the denominator, but why is this not natural log? Okay, natural log is only for a variable raised to what power? In the denominator. If it was 1 over h to the first power, then it'll be natural log, right? But if it's any other power, I got to bring it up to the top, okay? So this is, rewrite this as 1 over h to the 1/2. Continue rewriting it to get it ready for power rule. Okay, so now we're ready. Power rule, add 1 to the exponent, divided by that new exponent. All right, what about the antiderivative of the right side? Yeah, good. So k will stay, right? It's just a coefficient, but 1 becomes t, but we also want to include what? Plus c, yeah. Okay, let's do a little bit of cleanup here. I'm going to force that 1/2 up to be a 2. Now, as soon as the c shows up, you're welcome to solve for c. But my reasoning is, I find that, yeah, so there, you always have two options. Either you solve for c as soon as you see it, or you can wait to the end to solve for c. And sometimes I do different things depending on where I find it the easiest to solve for c. Here, I prefer to solve for c at this point because this is a relatively nice or clean looking equation, right? There's no square roots, there's no fractional denominators. But if I were to solve for h, that's what would happen first. If I were to solve for h first, I would have to divide by 2. I got to square both sides. It feels a little messier, feels a little bit cleaner at this point. So for this problem, I would prefer to just solve for c because it looks like algebraically, numerically, it's going to be a little cleaner that way. Now let's look at some ordered pairs that's provided for us here. We're given some ordered pairs. Depth of 16 meters at time t equals 0 and 4 meters at time t equals 30 when t equals 30 minutes. We know that this is not in terms of x and y. Our points are in terms of t and h. All right, so I'm just going to go ahead and kind of organize my ordered pairs here. I have 0, 16, right? Time t equals 0. We have 16 meters. And then at time t equals 30, 4 meters. Just organizing my information here. Now, again, we have two order pairs because we have two missing information that we're looking for. We're looking for K and we're looking for C. Now, if we're choosing between these two order pairs, which one do you think would be the more favorable one to start first? Okay, why 0, 16? Yeah, 0 is very, very helpful, right? 0 is going to take out a variable for us, allowing us to solve for the other variable a lot faster than we're dealing with 30 and 4. Chances are we're still left with two variables, but the 0 is going to do the job of eliminating one of the variables and solve for the other one. Okay, so we're going to start with 0, 16. Always take advantage of that information if they give it to you. Okay, so 16 in for H and 0 in for T. Okay, that's good. K is going to go away. We can isolate C. Careful with order of operations here. What do we do first? Do we do 2 times 16 first and then take the square root, or order of operation exponent comes first, right? We got to do the square root of 16 first, and then we turn around and multiply by 2. So square root of 16 is 4, and 4 times 2, 8. Okay. Okay. Once you have your C value, you're going to go back and update your previous equation. And now that I have my updated equation, I'm going to turn to my second order pair and see if that can help me out. Thank you. Okay, so 30 in for T, 4 in for H. Okay, square root of 4 is 2. 2 times 2 is 4. Okay, subtract 8 from both sides. Okay, divide both sides by negative 30. So now that we have our K value, we're going to go back and update it so that we have an equation that has both the K and the C replaced with numeric values. Okay, so insert this 2 over 15 where this K is. Okay, so now we're almost there. We just have to solve for H, right? So solve for H, I got to deal with two things here. I got to move this 2 over to the right side, and I got to deal with this 1/2. So I'm going to divide by 2, but divided by 2 feels messy because I have to deal with the complex fraction. So rather than dividing by 2, I'm going to think of it in terms of multiply by 1/2. It just feels more straightforward that way, not as messy having to deal with a fractional complex fraction. So multiply everything through by 1/2. 1/2 is going to do the job of eliminating the 2 from the left side. Okay, 1/2 times negative 2 over 15. The 2's can cancel out. We're left with negative 1 over 15 t. And then 1/2 times 8 is 4. Okay, one last thing to do. What's our last thing that we can do to solve for h? Yeah, square both sides, right? Right now, the left side is showing square root, so if I square both sides, I can get that radical to go away. Now, on the AP exam, if you can solve for your variable, if you can get the variable by itself, it doesn't matter what the right side looks like. Just leave whatever mess you see on the right side alone. Don't try to think in terms of, oh, do I need to expand? Do I need to clean up? Do I need to find common denominator? If you can get that variable by itself, you're done. Okay. Don't try to do anything on the right side, right? And also in the AP exam, if it's non-calculator portion, you're never required to simplify your answer. So as long as you have a numeric version of the answer that's equivalent to the correct simplified version, go ahead and stop, right? I think the only thing is, if you see a trig expression that needs to be resolved, you need to resolve it. So if you see like cosine of pi, you do need to convert that to a -1 to get full credit. But in terms of fractions, common denominators, and complex fractions, you can leave all that alone. Okay, any questions here? All right, let's look at a Riemann sums problem, page 18. I'll leave this up here for another minute or so. Go ahead and read number 2 on page 18. It should feel like a lot of the steps that we've seen with Riemann sums. Okay, page 18. On the Saturday before Mother's Day, drugstore has a large selection of greeting cards for sale. Between 0 and 10, between the hours of 0 and 10, number of cards left on the shelf is changing at a rate of m prime. So we see that cards are leaving the shelf at this rate. The function m is twice differentiable, and m of 7 is 44. Okay. Part A, approximate m double prime of 6. So m double prime of 6, we have m prime. We're looking for m double prime. Ideally, we will be able to find the derivative, but we can't find the full derivative because we don't have an equation for m prime. So the next best thing is what? Slope. Yeah, so choose the two closest order pairs to our target. So 6 falls between 5 and 7, so we'll use these two order pairs. Okay. So change in m prime over change in t will give us m double prime. And what's our unit of measure going to be? Yeah, cards per hour squared. Yeah. Okay, careful. Watch out for your negatives there. Make sure you keep track of them. You get a positive rate there. All right, part B, using correct units, interpret the meaning of m double prime of 6 in the context of this problem. So second derivative, right? I know that typically we like to use the words velocity acceleration, but that doesn't make sense for this context. So how can we use words to interpret what that m double prime is telling us? What is that m double prime of 6 equals 1 tell us about the situation that's going on here? So I think in terms of second derivative as what a rate of a rate, right? So that's what we want to be able to represent. So we want to say that the rate is increasing, right? That positive there. So when you see the words, when you involve rate and increasing of a rate, you're essentially talking about a rate of a rate. Okay, so this is the type of wording that that AP exam, College Board is looking for when you're interpreting, when you're looking for these word problems, when there's time involved. This is the way to say it. M double prime of 6 equals 1 means that the rate at which the cards left on the shelf is increasing at 1 cards per hour squared. Okay, part C, write an equation of a line tangent to M. So we've been doing this over and over again, right? Tangent equation. So get your order pair, get your slope, point slope form, and then linear approximation. Okay, so your order pair comes from the description in the paragraph above. And then the tangent line m prime of 9, m prime of 7 comes from your table. Also, you have to make adjustments with your variables, right? Instead of x and y, we're using t and m. Part D, is there a time somewhere between 0 and 7 such that m double prime of c is equal to 0? Okay, now we don't have m double prime, so we can't look at m double prime and look to see, we can't do IVT here and look to see if there's a value above and below 0 and that graphs and across to 0. But we do have m prime. So what's the relationship there between m prime and m double prime? M double prime is the slope or derivative, right? So we're looking for where derivative or slope is 0. That's kind of like a hint, right? Which theorem is that? Rolle's theorem, right? So Rolle's theorem, what's required though for Rolle's theorem to for us to be able to do Rolle's theorem? We need 2 points to be what? The same, right? So 0 and 7 doesn't quite show us that. So, but it says, is there anything between 0 and 7 where we can guarantee that slope 0? Do you see where we can guarantee that slope 0? Between what? Yeah, 4 and 7, right? 4 and 7. You see that m prime starts at -12. It's going to go down. Maybe it goes down further than -14, but either way, it's going to have to come back to -12. So then along that path, it's got to have a slope 0. And also, we're told that the function is differentiable. So that tells us that it's a smooth curve. We can go through each of our conditions. Okay, so Rolle's theorem is going to apply. We can guarantee that slope 0 in that interval from 4 to 7. Now, notice that Rolle's theorem, we have to make an adjustment with Rolle's theorem. Right? Typically, we're trying to find out where f prime is equal to 0. But because everything we're given is in terms of m prime, we can guarantee that m double prime is equal to 0. So we should make an adjustment, right? Still, Rolle's theorem is just everything shifted down one derivative. It's the slope of m prime that we're guaranteeing, not slope of m. Okay, part F, pretty straightforward, right? Riemann sum. So 4 subintervals, go to your table, and then start marking off your intervals. Subtract your x's or subtract your hours, and then you can get the width, and then you can pull the height from the second row, and then do width times height. So there are my widths there. 0 minus 1, sorry, 1 minus 0, 4 minus 1, 5 minus 4, 7 minus 5, and then take each of the widths and attach it to the appropriate height. We're doing right Riemann sum, so 1 times -10, 3 times -12, 1 times -14, and 2 times -12. Okay, that -84, that tells us how many cars have been removed from the shelf. So over the 7-hour period, by Riemann sum estimation, 84 greeting cards were sold or at least taken off. Okay. Part G. Evaluate the definite integral from 0 to 1, m double prime of 7 minus 3t. We saw something like this on the previous quiz, right? We know the integral of m double prime will rise up to m prime, but then before we do that, we have to take care of that 7 minus 3t. So what procedure do we have to go through? Not quite cleaned up yet, so what needs to come first? Seven minus 3t is what? Is our u value, right? U substitution. Right. So go through u substitution. Okay, we let the u value be that portion inside the parentheses, 7 minus 3t. We make everything in terms of u, so we can get that cleaned up. Du dt is -3. Solve for dt. We get du over -3. And we're just substituting the parentheses and dt. See what left over we have. dt gets replaced with du over -3. So that's an indication that, okay, we got to keep track of that coefficient there. We can push that du, that -3 out as what? Yeah, -1/3, right? -1/3. And now we're ready for our first theorem, ready for our antiderivative process. Okay, everything is cleaned up now. M double prime will rise up to M prime. The -1/3 just tags along. So integral of M double prime becomes M prime. Once you take the antiderivative, the integral notation and du notation drops out. Right. And now we're ready to involve the bounds. But one more thing, let's get that u value replaced back in terms of t, so we can be able to have matching variables there. Bring the u back in terms of t, and then we can work the bounds in. So upper bound first, minus the lower bound. But we can M prime of 4, M prime of 7. Those are all values we can pull from the table. Okay, we got there 17 and 18. Your homework is page 19 to 20. I'll send out a reminder on Sunday. Monday, we'll do just the same thing here, review between these two FRQs, and Tuesday quiz.